All right, today we're going to talk about one of the more interesting things in differential equations, and those are Laplace transforms. And they're one of those things that this first lecture is just basically to introduce them to you and why they're useful. There's going to be a lot of hand waving at the beginning where you just got to trust me on why certain things work and why we're doing what we're doing. But first, here's an example. We're going to start with an example that is kind of beneficial as to why you would want to do a Laplace transform versus, say, actually solving it. So this is kind of similar to one of the problems we did in, I think it might have been chapter 3 or chapter 2. I'm not sure. And the difference is beforehand we only did a single valve, water was coming in, and it had a consistent mixture the whole time. Now what's going on is as time after 10 minutes, now we're on to a different valve that is releasing water with half the amount of mixture. So your concentration looks something like this. You're constantly dumping in 0.4 kilograms, and then you make a change at 10 minutes. This should be closer to like back here. And then the nice thing is, though, 6 liters go in, 6 liters come out, so there's a constant amount of water in the tank. The only thing that's changing is the amount of solution. So the amount of fluid in the tank is just constant. Doesn't change. How long will it take to replace the initial amount of fluid? Well, if it's got 1,000 liters at the start and it's having 6 replaced every minute, then whatever 1,000 divided by 6 is, that would be how long it would take. So let's say we need to come up with a function that talks about the amount of salt coming into the tank at any time. So one thing to take into account is we have 6 liters per minute and we're dumping 0.4 kilograms per liter. So basically what we're going to have at the start is 6 liters a minute multiplied by the 0.4 kilograms per liter to give us 0.24 kilograms per minute for the first one. And that's when we'll say time is between 0 and 10 minutes. Then similarly, you would multiply the 6 liters per minute times 0.2, and then you would get that it's 0.12 kilograms per minute if t is greater than or equal to 0. So kind of like what we did before, the only difference is now we've introduced a piecewise function, and those are never fun to deal with. So how is the amount changing? Well, like a classic compartment problem where you have in and out, it's the amount that goes in minus the amount that goes out. So in our case, the amount that goes in is, I'm having to hold up notes for this one because there's a lot to keep up with. Our amount that goes in is g of t. And our amount that goes out is the 6 liters per minute times, this is where you have to be careful, times X kilograms, that's how much is in there at the given time. Because remember, this is the concentration of salt in the tank divided by the initial 1,000 liters, which means that we have G of T minus 3, not 6, 3/500ths X. So, now you notice if we move it over, we get X prime times 3/500ths X equals G. So it kind of looks like a standard first order where you have an f of t times x prime, or an f times x, and then you do the differential. Not linear. The word is escaping my mind, and I'm not going to remember it. At least not now. I'm going to be at the very end of this video and just shout it, probably because it'll pop into my head then. But the problem is, even if we did say find that integrating factor, how do you deal with a piecewise function? That's 10, not 30. Now, you probably know exactly where I'm leading with this, because this is a section about Laplace transforms. I just gave you an ugly problem, so let's talk about Laplace. Now, the Laplace transform, basically what it does is it's a mapping, like any function is. But what these functions do is they take a problem in one domain that's hard to deal with, and then map it into what we call the S domain, which is very easy to deal with. And this is always the equation for a Laplace transform. 0 to infinity, e to the negative st times f of t. And f of t is what you're doing the Laplace transform of. So if it was L of sine of t, this would be integral from 0 to infinity, e to the negative st times sine of t dt. And if I remember correctly, Laplace transforms actually, I don't think they were initially intended for differential equations. I think there was actually some use for probability with them as well. I may be way off base with it, but from what I remember reading, I think there was some usefulness in different areas other than just differential equations. You kind of, because these are made up of linear, Laplace transforms are made up of linear components, you get the nice fact that they're linear. So like the same way you could do, just an example, and I can't draw the L like that, so I just draw the L like my last name. I'll do, if you do the Laplace transform of a times f of t plus b times g, then it's just a times the Laplace transform of f plus b times the Laplace transform of g. And if you were to plug af plus bg into this equation, it would be very easy to see how you're able to factor it and use, not the best way to put it, but just use the easiness of integration already being linear. So we're going to, kind of like we did with, if it was too difficult to deal with all as one whole, break it up into different components. So what we're going to do is we're going to integrate and we're going to take these piecewise component, or not piecewise, but we're going to take these components, mix them together, and then we're going to get our Laplace transform. Basically, break it up into smaller pieces, Laplace transform each one, and then you'll get something that's a little bit more usable. Now, the Laplace transform of x is always going to just be x of t is just some function. What we do, though, is we call that function x of s. And then if you were to do the Laplace transform of the derivative of x, you're going to get this factor of s times, whoops, this should not be x of x, it should be x of s. And if you wanted to prove that, you could use integration by parts on the first one, and you would see those components kind of pop out where they need to. So, this is where I might be slightly distracted because I have to use, or to go back and forth on notes. So if I were to take the Laplace transform of this whole thing, so that's going to give me, because we've already got it solved, that makes life a little bit easier. I'm going to get s times x of s, because it's derivative. Go back to here, where capital X is the Laplace transform of lowercase x, minus lowercase x of 0, which was our original, and then plus, remember I said it was linear, so 3/500ths times the Laplace transform of x of s, and then we don't know g, so that will also be the Laplace transform of g of s. So part of what works out nicely, remember this, that at the initial point 0, we had that it was 30. So we get 30 that we can plug in. So I get s x of x, x of s, plus 3/500ths capital X of s. And you can kind of see what I'm doing here. I'm going to add the 30 to both sides. So then I get g of s plus 30. Now I would factor out x of s and then just divide out the s plus 3/500. So that gives me x of s is equal to g of s plus 30. All that divided by s plus 3 divided by 500. To which at this point you're probably going, great. What do I do with that? Now the nice thing is, if I have x of s and I can solve what g of s is, then it's kind of like knowing the inverse. If I can, basically what I'm going to do is I'm going to map it into one plane, play around with the algebra over there. I'm going to have to do a little bit of calculus here, but then once I do that, all of a sudden, life's good, because now I'm just off in, not La La Land, but I'm off in just dealing with this. I don't have to mess with, what's the right word? I don't have to go through a differential equations method. All I'm doing at this point is, we'll call it simple integration. and just solving for x, capital X in this case. Now the reason I say that g of s is important is I'm going to kind of break this up into a new section. Remember, g of s is equal to the Laplace transform of lowercase g of t. So that means this is the integral from 0 to infinity of e to the st times g of t dt. Now, this is why it was important to map it into this plane, because if I go back to what g of t was, remember it was this piecewise function. So we're going to integrate the piecewise function, which means split your integral at the different points in the domain. So integral from 0 to 10, e to the st, and then that's going to be multiplied by 0.24 with respect to t, plus integral from 10 to infinity, e to the st, times 0.12. So what that gives us is that it's equal to, so 0.24 is a constant, but we're going to have to divide it by s because that factor is going to come out from here, not from 10 to infinity, that's the next one, from 0 to 10, plus 0.12, also divided by s for the same reason of integration. Oh, these are negative s, which is going to make this and this, because I'm too lazy to go back and just put it as a minus sign. So that's going to equal, and this is where it's going to get a little messy. So negative 0.24 divided by s. I'm doing my best to make those look like s's and not 5s, times e to the 10s plus 0.24 divided by s, and then plus, nope. Actually, it really doesn't matter here because now I'm going to get basically plus 0 because this is e to the negative st. And so that's going to be e to the negative s, throws it in the denominator as it goes to infinity. The whole thing goes to 0. And then plus 0.12 over s e to the 10s, which will give us .24 divided by s minus 0.12 over s e to the 10s. Negative 10s. I'm going to get this right eventually. But so that gives us what g of t is, or the Laplace transform of g of t. So now our piecewise function is a algebraic expression. And so if I plug all that in, we get that x of s is equal to, I'm just going to have to read it off from here. And I'm going to split it up 30 over s plus 3/500ths plus s times s plus 3/500ths. And that would be under 0.24 minus, same denominator, but again, because the way these work, We're going to split it apart. And then that one's divided by, or under 0.12 e to the negative 10s. And now this is where the Laplace transform is useful. After doing this, what I have to go off of is there are Laplace tables of just some common Laplace transforms. So what you do is you go to that, you go to your table and use a little bit of the theory. And so if the Laplace transform went from the t domain to the s domain, then the inverse Laplace transform will take your function from the s domain into the t domain. And after you do that, like I said, this is the hand wavy moment. You get, with absolutely no differential equations formulas applied, 200 minus 170 e to the negative 3t over 500 minus 100 multiplied by 0 when t is less than or equal to 10, or 1 minus e to the negative 3 times t minus 10, all divided by 500. And that's if t is greater than 10. And that's the hand waving, because at this point, all I've shown you is what the Laplace transform formula is. I have not shown you at all how do you get back to it. But this is what it's meant to illustrate, this first one. I don't have to go through and find this differential equation. I don't have to solve it. And again, I don't want to deal with a piecewise in my differential equation. Differential equations are messy enough as is. Bringing in a piecewise function is just, I don't know, you're a glutton for punishment. So the Laplace transform makes this a lot easier. Because it's like I said, it took our equation, which was a very ugly looking differential equation, and all I said was, well, what if I just do the Laplace transform? And I don't even look at what the functions are. Because again, sometimes you don't have the function. I mean, that's the whole point of the differential equation, is you know how the function interacts and you want to solve it. So we did the Laplace transform, and we got what the Laplace transform of x was. Then, like any good function, you map it into a domain where it's easier to deal with. You solve it in that domain. You get what it is, which was the first line. And then you do the inverse transform to bring it back. And like I said, this is just purely intended as a introduction. This is not in any way, shape, or form expecting you to be able to go from x of s, capital X of s, I should say, to lowercase x of t. That's not what it's intending. What it's intending is to show the usefulness of it. You'll be able to do the Laplace transforms and the inverse Laplace transforms soon, but this is just meant to illustrate their usefulness. So just read through those sections, take a look at those homework problems, and then 7.2 will actually get into kind of like common Laplace transforms and what does and what does not have a Laplace transform.